In this video, we're going to be looking at forms of energy. The basic forms of energy and those specifically that we'll be looking at in chemistry, plus we'll be doing a simple kinetic energy calculation and conversion of energy units. Energy is the capacity to do work or transfer heat. The basic forms of energy are kinetic energy and potential energy. Kinetic energy is the energy of motion. Potential energy is the energy of position. If we look at kinetic energy, the base formula for kinetic energy is going to be energy kinetic equals 1/2 times the mass times the velocity squared, or often given as Ke or e to the k equals 1/2 mv squared. In chemistry, the kinetic energy we're going to be dealing with mostly is thermal energy, energy associated with the random motion of atoms or molecules. Potential energy, the energy of position. In chemistry, we're going to be dealing with two potential energies. Chemical energy, the energy that is stored in the bonds of chemical compounds. So when we do a chemical reaction, we're going to be either creating or breaking bonds, and there's an energy associated, potential energy, in these chemical bonds. The other is electrostatic energy. Electrostatic energy is the energy that results from the interaction of charged particles. If we think about a positive and negative charge, they're going to be attracted to each other. If we think about two negative charges, they'll be repulsed. The equation for this is E to the EL is proportional to Q1, the charge of the first particle, times Q2, the charge of the second particle, divided by the distance between the two particles. When we do this calculation, if the electrostatic energy is a negative, then that's an attraction. If we have a positive and negative charge, we'll end up with a negative electrostatic energy. That's an attraction. If electrostatic energy equals positive, then we have a repulsion. We would get this if we had two positive charges or two negative charges. The other basic information we need to know about forms of energy is the SI unit of energy. The SI unit of energy is joule, given by capital J. The units for joule is 1 kilogram times meter squared divided by second squared. This because a joule is defined by a 2 kilogram mass moving at 1 meter per second. If we put that into our formula, Ke equals 1/2 mass times velocity squared, we come up with joules. We also have a very common non-SI unit for energy, calories, given as cal. This is the energy required to raise the temperature of 1 gram of water from 14 degrees Celsius to 15 degrees Celsius. 1 calorie is equal to 4.184 joules. This is a defined number, and so therefore it's exact. This is important when we think about our significant figures in these calculations. Now let's look at two simple problems. First, a kinetic energy problem, and then a conversion problem. First problem. Calculate the kinetic energy of a hydrogen atom moving at a speed of 125 meters per second. Remember, our formula is going to be Ke equals 1/2 mass times velocity squared. We're going to be looking for kinetic energy, and it tells us that we have a hydrogen atom, so our mass is going to be the mass of the hydrogen atom, and our velocity they give us as 125 meters per second. Now our value should be in SI units, and this is going to help us get all of our units in the correct value to get joules. So a joule is, remember, a kilogram meter squared divided by second squared, which means that we're going to have to get our mass into kilograms. Let's start by looking up the mass of hydrogen. Mass of hydrogen in atomic mass units is going to be 1.0079 AMUs. So if we do our conversion, remember we need to get this in kilograms. We'll start by taking that, multiply the unit for 1.661 times 10 to the minus 24th grams for an atomic mass unit, and then we can convert grams to kilograms by using the definition of 1,000 grams per 1 kilogram. Do our math on that, and we will get 1.674 times 10 to the minus 27th kilograms. Now we just need to take this value and plug it into our formula. So Ke is going to equal 1/2 1.674 times 10 to the minus 27th kilograms times 1.125 meters per second squared. Do our math on that, and we'll come up with 1.308 times 10 to the minus third joules. Joules are actually small energy terms, so this will often be converted to kilojoules. We can do that simply by understanding that there's 1,000 joules in 1 kilojoule. But for this equation, we'll just leave it in joules. All right, let's look at another problem. Calculate the number of calories in 681.4 joules. Simple conversion, but again, many scientific disciplines still use calories. So you'll see the conversion between joules and calories quite often. So we know that 681.4 joules, we're going to need a conversion factor. We know that 1 calorie is defined as 4.184 joules. We can do our calculation. We get 162.9 calories. Now for this one, notice that we have 4 significant figures to start with. Since 1 calorie is equal to 4.184 joules by definition, that means it's an exact term, which means we have as many significant figures as we need for that value. In this case, they're both 4, so we'll have 4 significant figures in our problem. 162.9 calories. You'll be doing more calculations dealing with chemical energy and electrostatic energy later. Simple kinetic energy problems are pretty straightforward. Just make sure you follow your units. And again, make sure that you remember that 1 calorie is defined as 4.184 joules when you do conversions from joules to calories or calories to joules.